Welcome to this lecture series in linear algebra. We will continue our discussion on matrices and let us recall some of the things that we will use. So, first we will talk about matrix of composition. Suppose we have three vector spaces U, V and W over a common field F, and let's say we have bases A, B and C of U, V and W respectively. Suppose we have linear maps from U to V and from V to W. Then the matrix of their composite with respect to the correct bases is the product of the matrices. So we defined the product of two matrices in the previous lecture. It was a grisly definition, but we stated this as a fact and left its proof as an exercise. Okay, a notational point. If T is an endomorphism on a vector space V and B is a basis of the vector space, then we write this to mean that. So we just don't write B two times. We just write it once. Okay, and one more thing. This is a small fact, a consequence of that one. If S and T are endomorphisms on a vector space V and B is a basis of V, then the matrix of the composite with respect to the basis B is the product of the matrices with respect to the basis B. So in this proposition, just replace A and C and B by just B and use this notation, you get this lemma. Okay, and one more notation is that if we have an endomorphism on this coordinate space, then we write simply this to mean the matrix of T with respect to the standard basis. Coordinate spaces come with standard bases, so we may just use it and compactify our notation. All right. So first we'll see a small application of linear algebra to matrices. Suppose we have three matrices A, B and C. All of them are in cross N over some field F. Then if you multiply A and B and then multiply the result with C, it's same as first you multiply B and C and then multiply the result with A. So this is associativity of product. If you multiply 2 with 3 and then with 5, you get the same thing as when you multiply 3 with 5 and then multiply the result with 2. So this is the matrix version of this very simple fact. Although if you want to prove it in the matrix setting, using the definition of multiplication of matrices, it is going to be a long exercise and a tedious one. But we will prove this using linear algebra. So how are we going to do it? So the main difficulty here is setting up notation. I want to associate linear maps with A, B and C and I'm not able to figure out what notation should I use. S, T and U are bad, so let me go for, maybe I'll go for P, Q and R. Very bad notation, but what can we do? So let P, Q and R be endomorphisms on this coordinate space be such that the matrix of P is A, the matrix of Q is B, and the matrix of R is C. So as we mentioned, all these matrices are with respect to the standard basis of this coordinate space. So we can find such endomorphisms. In fact, there are unique such endomorphisms. There is only one P which satisfies this, only one Q which satisfies that, and so on. Okay, and now we know we have that you can compose P and Q first and then compose the thing with R, or you can compose Q and R first and then compose the thing with P. So this equality is just a set theoretic equality, nothing to do with linear algebra. If you compose three maps, you can compose the first two and then compose with the remaining, or you can compose the last two and then compose with the first. Purely set theoretic identity, and now we just convert this identity to a matrix identity. And to do that, we just take matrices of both sides. Right? But now, matrix of composites become matrix of product, which gives another application of the same result. which is exactly what we wanted to prove. So this is A times B multiplied with C is equal to A multiplied with B times C. Right? This is A, that is B, and so on. So very simple. So this displays the power of linear algebra a little bit. Okay. Another application, if you will. So first, a very simple exercise. Fix an endomorphism and let B be a basis of the vector space. If matrix of T with respect to the basis is identity, then T itself is identity. Note that this symbol I has been abused. Here I represents the identity matrix. So the identity matrix is an n cross n matrix where the diagonals have 1, all of the diagonal entries are 1, and all the other entries are 0. So that is the identity matrix, but here the identity symbol is denoting the identity transformation or the identity endomorphism. Okay, and the proof of this is an exercise. If matrix of T with respect to a basis is identity, then the endomorphism itself is the identity. Okay, what about this one? Suppose we have two matrices, n cross n over some field F, and suppose we find that their product is identity. Then magically the product in the opposite way, in the reverse way, is also identity. And if you try to prove this just by definition of matrices, just by definition of matrix multiplication, I'm pretty sure you will fail. It's kind of a magical thing that this happens. But if you look at it with the lens of linear algebra, this will no longer be any mystery. So let's prove this. So again, we will pick endomorphisms on this coordinate space such that the matrix of S is A and the matrix of T is B. Here the matrices are with respect to the standard basis. Okay, we are given that A times B is identity, which is same as matrix of S times matrix of T is identity. I should write matrix of identity, but matrix of identity we also write as identity by a small abuse of notation. Okay, but matrix of, or the product of matrices is matrix of composite. This is what we recalled earlier in the beginning of the lecture. So this is identity, but by the previous lemma, this means that ST is identity. Okay. And now by linear algebra, what we learned in linear algebra, if ST is identity, then TS is identity. If you compose two endomorphisms and you get identity, then composite in the reverse order is also identity. So that's the linear algebra step, and now you again convert this into a matrix equation. And we get B times A is identity. All right, nice application of linear algebra. And now we get to business of this lecture. So we want to define the inverse of a matrix. Suppose A is some n cross n matrix. We say that it is invertible if there is some matrix B, n cross n again, over the field F again, such that A times B is identity. All right. Now by the previous lemma, this equation is same as saying that B times A is identity, but I don't want to write some redundant thing. So we have defined what is meant by an invertible matrix. Let us show that, let us first consider this lemma before we proceed. Suppose we have three matrices, n cross n over a field F, and suppose A times B and A times C are both identity. Then we want to show that B is equal to C. So if there is a B in this definition, if there is a B such that this happens, then there is only one such B. There may be no such B, but if there is one, there is only one. Why can we say that there may be no such B? Well, if you take A as the all zeros matrix, every entry is 0, then there is no such B. And that is only just one example. There are infinitely many examples. Okay. So what about this lemma? Well, very simple. We have that A times C is identity, which implies B times A times C is identity, which implies B times A times C is identity by the previous page where we, or maybe not the previous page, but whichever page where we discussed composites, matrix multiplication is associative, which implies identity times C is identity. Why? Because we know that A times B is identity, and by the previous page, this means that B times A is also identity. So we have that, but this gives that C is sorry. Here I meant to write a B. So this is B. Once again, we had this equation, we just multiplied by B on both sides, and then we use associativity of product. We wrote this thing as that thing, and B times A is identity by the previous page because A times B is identity, and therefore C is equal to B. Sorry for the little slip there. Okay, and now we can define what is the inverse of a matrix if one exists. So suppose A is an invertible matrix. Look at this definition. Suppose A is an invertible matrix, then the inverse of A is a matrix B such that A times B is identity. Since we just showed that there is only one such matrix if at all one exists, in fact if A is invertible then one exists by definition, so we can write the inverse because there is only one. Okay, and let's finish this slide by this lemma. Fix an endomorphism, let B be a basis of the vector space, assume T is invertible, then the matrix of the inverse with respect to the basis B is the inverse of the matrix. So yeah, I should define this notation. We denote the inverse of A by this symbol, right? So if you have a invertible matrix, then you can denote its inverse like that. So our claim is that matrix of the inverse is inverse of the matrix. And the proof is just one line. We have T inverse T is identity, which implies matrix of, well, let me write TT inverse is identity, doesn't matter, it's the same thing. So that implies matrix of TT inverse with respect to B is identity, which implies matrix of T times matrix of T inverse is identity, and therefore this is the inverse of that. That's it. The matrix of inverse is inverse of matrix. Okay. Now for the final slide, change of basis. Fix an endomorphism. Fix two bases of the vector space. A natural question arises. One can form the matrix of T with respect to the first basis and the matrix of T with respect to the second basis, and we ask an open-ended question as to how can we relate these two matrices. Surely there must be some relation depending on how these two bases interact. For instance, if these two bases are the same, then these two matrices are also the same. So there must be some way to connect this with that, and that is what we are going to do and finish this lecture. So let B be this basis, and we are just setting up some notation. Okay, and let S be this linear map. Right, so S is the linear map which sends V1 to V1 prime, V2 to V2 prime, and dot dot dot, Vn to Vn prime. And one can note that S is a linear isomorphism. Take that as an exercise if it is not immediately clear. Okay, and now say T of Vj is what I'm going to write, I'm going to explain this. So T of Vj is some vector in V, and any vector in V can be written as a linear combination of these people because they form a basis. So let's say these are some coefficients whose corresponding linear combination outputs T of Vj. So this is for all j, of course. So this is same as saying that matrix of T is the same as saying that matrix of T with respect to B is the one whose ijth entry is Aij. Right? Yeah. Now, this can be, we just note that Vj is S inverse Vj prime by definition of S. Right? Now we apply S on both sides. Maybe I'll apply it on the equation above for brevity. Right? We just applied S on both sides and now it becomes, the left side is this and the right side is, we use linearity of S to get that. Alright, but what is S of Vi? S of Vi is Vi prime, so let me just mess it here itself. Alright, great. But what does this equation now read? This equation just reads that the matrix of STS inverse with respect to B is the same as this guy, just by definition of matrix of an endomorphism with respect to a basis. So this matrix is same as that matrix. Therefore, the matrix of STS inverse with respect to B is matrix of, sorry, this is with respect to B prime, I messed up. This is a B prime. Sorry about that. So matrix of STS inverse with respect to B prime is matrix of T with respect to B. But what is the left-hand side? The left-hand side is this product. And the right-hand side is what it is. Alright. But now we use the result about inverse of a matrix. The matrix of the inverse. So the matrix of the inverse of S is inverse of the matrix of S. And again, I missed a prime here. And let's just call this matrix P. Let's just call this matrix P. So we can write P matrix of T with respect to B prime. P inverse is that. That's it. So the relation between these two matrices is via this conjugation relation. We call it conjugation. There is a group, that is a group theoretic notion. So P is the matrix of S with respect to B prime. Okay, so with that I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.